Okay, people, let's get started. Now, you'll remember that today's lecture is not on the midterm, all right? Not on the midterm. And I want to apologize in advance because at the end of the lecture today, I've got to uncharacteristically have a 12 o'clock, so I'm not going to be sticking around. I'm going to sidle out the door, okay? So sorry about that. Today, we're going to talk about fresh water in a changing climate. And for many people, this is the big environmental problem. But the punchline today is that it very much depends on where you live. And as we'll see later in the course, there is something we can do about it. So water scarcity is a regional problem, a critical, in some cases, life and death determining regional problem, but it is not a global problem. Globally, there is plenty of fresh water, clean fresh water for people to drink. The problem is only, and this is, well, it's like saying, the problem is only cancer. The problem is only distribution, all right? So the hydrologic cycle looks like this. I'm not going to expect you to know these numbers. But I do want you to notice that the numbers here, that's 284,000 kilometers cubed of precipitation, okay? Now, a cubic kilometer, if you do the math, and remember that a liter is a kilogram, and a cubic meter is a metric ton of water, right? So metric units are defined based on water. A cubic kilometer is a billion metric tons or a gigaton, the same units we use for CO2. And you'll remember that humanity's release of CO2 to the atmosphere every year is around upper 30s gigatons. CO2 equivalent, if we include all the greenhouse gases and their warming potentials, is above 50. But that number of just precipitation over the oceans is 284,000 gigatons. So the point I want to make here is just that CO2 is a rare trace gas. Water isn't. Okay, there is a lot of water moving around. And a lot of times people ask, well, aren't we going to run out of water if we do X? All right. What happens if we make hydrogen from electrolysis to burn? Aren't we going to run out of water? And the answer is no, you're not going to run out of water doing that, because these numbers are in the hundreds of thousands of gigatons, and the kind of numbers we're talking about are in the gigatons, all right? So 5 orders of magnitude down. There is precipitation over land and evaporation from land are different by quite a number of cubic kilometers, and that's because 36,000 runs off and goes into the ocean as rivers, and so on. And so there is more rainfall than evaporation from land, and there's more evaporation than precipitation over the oceans. And the amount of water on the planet is, to a first approximation, fixed. Given the amount that flows, it's all cycling and no inputs and outputs. There's a little bit that comes from chemical reactions where the water is locked up in some rock, or is produced the same way that when we do electrolysis of water, we make some hydrogen and oxygen and we can combine them to make water, but this is a tiny amount. Now, this is a diagram from this paper on so-called planetary boundaries by Rockstrom et al. I'm not a fan of the paper, I gotta tell you, but it's widely cited, and so you may see planetary boundaries referenced. They have this diagram that they use, and if you exceed the outer boundary here, you've exceeded the Earth's normal functioning capacity. You're outside the planetary boundary, okay? And if you're in here in the green zone, you're in the safe zone, okay? And you can see that biodiversity loss is outside normal functioning for the planet. And that's true. It's 1,000 times bigger than the background from the fossil record. The nitrogen cycle, we actually fix more nitrogen into fertilizer biologically, so you need nitrogen because all of your catalysis and much of your structure is made out of proteins. And proteins are made out of amino acids. And the word amino means there's a nitrogen molecule, nitrogen atom in the amino acid. And so the nitrogen is necessary for catalysis, and it's limiting in most ecosystems. Plants don't have enough of it. There's specialized microorganisms that evolved more than 3 billion years ago that pull it out of the atmosphere, but it's expensive to do, and put it into a form where organisms like us can use. We do that now to create chemical fertilizers to feed the planet. And the amount that we do in that way exceeds the planetary input rate through geologic time. So we're much bigger force in the nitrogen cycle than the planet. The climate crisis is starting to punch out here. Freshwater use, you see, is well on a planetary scale within the safe zone. All right, and that's the message, is that freshwater use is not a global problem, even from a group like the Rockstrom et al. Group, who are quite concerned about a lot of things, with reason. So I showed you this diagram in the first lecture, and it's kind of neat, you know. Total amount of water is here. The amount of water, the volume of the water is comparable to the volume in the atmosphere, a little less than the volume in the, about the same as the volume in the atmosphere. Liquid fresh water is here, and surface fresh water, stuff we can access, is that tiny little dot. And that tiny little dot looks teeny weeny at planetary scales. And you think, oh my God, it must be limited, right? But it is also 1 times 10 to the 17th liters. 1 times 10 to the 17th liters. The small fraction of the total water, a 10,000th the total water, but it's still 1 times 10 to the 17th liters, right? Which is a lot of liters. Now, how much do we need? How much do we use? So here's US water consumption rates, and I'm using US water consumption rates. Oh, I also want to just, before I do anything else, I wanted to just let you know that I want to credit Dr. Catherine Riamaki, who used to be at Princeton. She was on the Council of Science and Technology. She was a learning and teaching expert, and she is also a really accomplished hydrologist. And so she used to give a lecture that is similar to this lecture, but not the same. And I've adapted a lot of her images from it. So I want you to know that I stole some of this material from Catherine Riamaki, who left Princeton within the last year. She's currently the head of an NGO that's concerned about clean fresh water. Okay. So how much do we need? We've got 1 times 10 to the 17th liters of fresh water at the surface. So if we take US piggy water consumption rates, and we scale it up to a 2050 population of 9 billion people. You say, let's suppose every one of those 9 billion is as piggy as the average American when it comes to water use. And the answer is total consumption is 3.4 times 10 to the 13th, all right? Which is 1/10, you know, it's order 1/10,000th, 1 times 10 to the 17th, all right? That's the critical point here. Although, so even if everyone becomes as flagrant a water user as people in the United States are today, and there are 9 billion people in the world, more than there are today, then it still will be the case that we're using 1/5000th of the fresh water that is kicking around near the surface. Now that's poor consolation if you live in an area where there isn't enough fresh water, right? Where your children are dying because they don't have access to clean water. And if you have to carry a jug of water to, 10 miles a day and so on. But nonetheless, this is as a scientific matter, this is a distribution problem, not a total amounts problem, which is not the same as the CO2 problem, all right? All right, so there is water scarcity in some places. This is a regional analysis of from the planetary boundaries group with different, where you have beyond the zone of uncertainty, high risk zones. And the freshwater one is there. Let's zoom in on it. That's what it looks like. And you can see that there is water scarcity, the red beyond the zone of uncertainty. In the American West, you don't have to be from California anymore to know what a concern this is within California. There are parts of Mexico, lots of dry parts of Mexico, parts of Central America, all right, in particular El Salvador, but also on the Pacific slope in general where it's dry. Northern China, India, parts of India, but large parts of India. You see how much of it there. It's quite dry, of course, in this part of India, right? The Middle East in general, the Mediterranean, North Africa, and Southern Africa. So those are the sort of hot spots. You can see there are also some red in Chile, a little bit along the Caribbean coast of South America, but critical water shortages are in the places shown in red, all right? And you can see what a small fraction of the globe it is, but of course, important parts of the globe, and some of them politically fraught. Okay, so what's the residence time of carbon dioxide in the atmosphere? Does anybody remember? That's something you should know for the midterm, which is the day after tomorrow. Residence time of CO2 in the atmosphere, anybody? Yeah. Yeah, that's right. And so it's a range of time scales, but you think of it as being centuries to a millennia. And what do you think the residence time? And so the answer is, what's the residence time of water vapor in the atmosphere? Any guess? Yeah. Yeah, it's certainly less than a year. And you can see atmospheric water stays in the atmosphere about 1.5 weeks, okay? So after water evaporates into the atmosphere, it's going to fall as rain like 10 days later, all right? At any one time, there's about 1 inch of rain hanging in the atmosphere as water vapor. You distributed it everywhere in the world, got rid of all of it. And that inch is coming back and forth, 1/10 of it, 10% of it every single day. So this is a very different sort of problem than the carbon dioxide problem, right? And the rate at which it's replenished is extraordinary, right? But also that's a tip-off that, you know, it's possible for air to get dried out, to dump its water load and get dried out, right? So it's possible for there to be stochastic fluctuations because so much is flowing in and out, little imbalance for a short period of time, and you could really have issues there. Now, there are parts of the world, right? So ice caps where water lasts for a long time, frozen in an ice cap. But the water that we're seeing at the surface, the rainwater, the water that's evaporating is pretty short. Lakes and reservoirs, it's 10 years. Soil moisture, it's 2 weeks to a year. River channels, it's 2 weeks. And so this is all timescales that are like weather timescales. And of course, that's not an accident, right? Water vapor, the energetics of water vapor, the condensation and evaporation of water vapor are comprise a lot of what we call weather. Right? This is just a little video that shows, probably seen something like it before, showing the rains coming into the Sahel and showing the vegetation responding from a satellite image. Okay, that just shows you, of course, the kind of twitchiness around the surface that variation in rainfall makes. This is seasonal variation in rainfall. The seasonal variation in rainfall is caused by the so-called Hadley circulation. You've seen this probably in high school. This is not going to be on any exam, but because the Earth is spherical, a sunbeam of a given width hits the land surface over a shorter distance at the equator than near the poles. And this means the energy input per unit land area is much higher at the equator than at the poles. And that means that it's hot here and hot air rises. And as it rises, it dumps its moisture because the pressure goes down and cools and spreads out in a nice little fountain that looks like this. And it's dry, it's dumping its moisture as it's getting cold, rising up into the atmosphere here. There's 70,000 thunderstorms a day around this region globally. And then when it falls down here, it's all dried out. And this is where the deserts are, those latitudes. Here's the important point. Because the Earth actually tilts on its axis, the place at which the sun strikes the Earth perpendicular to the surface changes with the season. You've got a globe here and you've tilted it, and now the sunbeam, where it hits it depends on where it is in its revolution around the sun. And so that thermal equator is moving up and down with the seasons. Up in our summer until the solstice, and then back down again, hitting the real equator in the equinox and coming down again. And that's what's going on here, okay? This so-called thermal equator is moving up and down and dumping water on the Sahel. So the Sahel fluctuates from being in this region to being in this region. Greens up when it's in this region, and it dries out when it's in that region. That's what's going on there. And that won't be on the final. Okay. So there's enough water overall for human needs. Right now, rainfall is highly variable across the globe and through time in any one place because the residence time of water in the atmosphere is so short. The implication is that engineering strategies are needed for coping with water stress pretty much everywhere. So even in places with a lot of rainfall, the rainfall is variable. Sometimes there's way too much, like we saw in New York in Hurricane Ida. And sometimes there's way too little, like we've seen in California for like the past forever, mostly, okay? So regional problems now and in the future. I'm going to talk about clean water, what water is used for, then talk about drought, and then talk about climate change. And if I don't get through all of this, I'll do it the next time I talk to you. All right, so what about clean water? The good news is this is really a success story, like the success story in reducing global extreme poverty. Again, that success story doesn't help if you're still a terribly poor person or a person who doesn't have access to clean water. But nonetheless, in the sheer sort of stony-hearted actuarial analysis, it is true that since 1990, 2.6 billion people have gained access to what are known as improved water sources that were improved by people to be healthier. There's still 663 million people without access to these so-called improved sources. Now, improved doesn't mean good. Improved means just what it says, better than it was. It's been engineered to give some access, like a well or some other access to people that is healthier than just taking it out of a river. And so there's still 663 million people without access to this water. And when you think about the global population, that's a number that is starting to be manageable. You could think about pinching that out, right? You could stop it if we decided to as a species. This is the sort of thing that an extremely rich person could even think about stopping, okay? This is a number that is possible to finish. The bad news is that 1.8 billion still live with water that is sometimes fecally contaminated, okay? And that, of course, then is a vector for disease, infant diarrhea, and a whole bunch of other killers, right? Especially young children killers. 2.4 billion lack toilets or latrines, and greater than 1,000 children die per day from contaminated water. So this puts into context what is meant by an improved source, okay? It's improved in the sense that it's not always fecally contaminated, but it is still occasionally fecally contaminated. Our water is too, all right? Our sewage treatment plants get overwhelmed. They dump into the drinking water sources and that sort of thing. but we have testing all the time. Then there's a government and there's a response, and then they tell everybody you have to boil your water, and you have enough fuel to boil your water, or they distribute water if you don't have enough fuel. You know, like after Ida, one of the biggest relief efforts was to take in bottled water because people couldn't boil the water because the fossil sources and the electricity were turned off. So in addition, 1.7 billion people live where water use exceeds recharge. And recharge means precipitation from the atmosphere or the refilling of groundwater that's extracted, right, from precipitation and rivers and stuff elsewhere. So 1.7 billion people are pulling more water out, or in regions where more water is pulled out of the water bank than is being put back in. And these are not just places with contaminated water. These include, for instance, most of the Central Valley in California and much of the American Southwestern agricultural region. 40% of people experience water shortage from time to time today. Does anybody know what this map is? John Snow in Colorado. This is becoming more and more famous. It used to be extreme. There's a lot of people shaking their head. Somebody want to say what it is? Anybody remember enough to, yeah, go ahead. Yeah, that's right. John Snow was the person that figured out finally that microorganisms cause disease. If you can believe it, there was a time when we didn't know that. It's thought to come from the air and that sort of thing. There's a cholera epidemic in 1854. John Snow obsessively went to every little tenement and figured out where people were sick. And the pattern initially was inexplicable. This building they're sick, that building they aren't. This, you know, this apartment's sick, that one isn't. He then put all of these on a map, and then the light went off when all of a sudden he realized there was a single pump, the Broad Street pump, that P in the middle here, that P right there, in the middle of what looked like the epidemic. And then when he looked more finely, there were 3 water companies vying for the people in London, and the sick people all came from one source. And then when he found what that source was, it turned out the big exit from the sewage main in London was just upstream of the intake for the water that these people were drinking. Okay, so they were just like a, you know, a recycling system for human fecal bacteria. And so this then caused the massive investment in industrialized countries in infrastructure to clean up water, and changed vital rates, that is survival rates of people. The average person, not just the few in the nobility, but the average person for the first time since prehistory. Okay, so they were stuck sort of at Paleolithic levels all the way until we cleaned up the water, and we essentially arrived at modern vital rates then, and haven't changed since. I mean, you know, lifespan is extended a little bit, but not a lot relative to what happened here. And, you know, it was a tremendous outpouring of investment in infrastructure for an environmental cause. Politicians in the United States competed with one another on how grand their infrastructure project was going to be to clean up the water. I may have mentioned this before, but Chicago is now facing the fact that in the 1880s, somebody ran on, we're going to put sewers into Chicago platform. There's maybe 1870s. And person won, and they took a block of Chicago at a time, what it was already a city, 5-story buildings covered with bricks, everybody working like crazy. And they dug underneath them and jacked up the entire block 8 feet, put the sewers in, and then packed dirt dirt in, and then went to the next block, and the whole city got jacked up 8 feet. Okay, and now they're having to deal with that. They're having to, it's like now it's old, right? So what do you do with it? So, but the point is, we did that all over the world in industrialized countries, and it's all because John Snow realized that you shouldn't drink poop water. All right, which we all take for granted now. I live by that rule. Don't drink poop water. Okay, so this is just another diagram showing that light blue is unimproved and dark blue is improved. Most of the unimproved sources are rural now instead of urban. There will be some, at worst, even in poor places, some pump in the streets that the government has moderate control over. All right, so this is primarily a rural problem, and it's also a rural problem in the United States. In the United States, we have a rural well problem, but it's mostly not fecally contaminated water, it's fertilizer contaminated water. There are lots of wells, for instance, Nebraska and Iowa, where the nitrate pollution in the well is enough to cause a baby to become lethally sick. There's a thing called blue baby syndrome, which is common, particularly in Nebraska and Iowa, where due to wells that become nitrate polluted with fertilizer. This simply shows that the prevalence of diarrhea for children under age 5 falls with income, a fact that should surprise no one, okay? And one of the things that amazes me about this diagram is how little it falls. Babies are prone to diarrhea anyway. If you're ever thinking about having children, remember this, right? Okay. This is from the Shockwave report, percentage of the population with access to basic sanitation, and that's the top 60% and the bottom 40%. And you can see that there are all kinds of countries out here in the yellow for which the bottom 40% just doesn't have access to basic sanitation. So although the global story is one of success, there's still lots of work yet to be done. That's the point. These are population without access to improved water. This is 2018. The sizes of these circles, the biggest circles here are 80 million people, medium size is 20, and the smallest is 1. You can see that there are people here in the Midwest in the United States who are being counted, primarily because they're living on wells that are drilled outside their house, which may be contaminated, as I said, with fertilizer. So there's a lot of people here, right? And this is a common target of philanthropy because you're helping real people who's like that you can visit, right? And so it's not abstract in some way, the way cleaning up, for instance, the climate is. At least basic water requires an improved water source within a 30-minute round trip, all right? And these are the people who lack, under 50%, have water within a 30-minute round trip, all right? And so in essentially the whole of sub-Saharan Africa, like half the people have to walk a long way to get to their water source, right? You've all known that probably since middle school, but this is the problem of the women carrying the water, right? And spending all their day carrying the water from the only decent source. Okay. So what's all the water used for? All right. So if you live in Southern California, you could believe that the water is used for showers and for washing your clothes, because that's what they're telling you not to do. They're also telling you not to water your lawn, all right? Telling you not to wash your car. But they aren't saying so much, we've got to shut down the almond groves, something like that, right? This is mostly telling people to use less water. And you've got to ask, why are they saying this? Are those really the big sources? And the first thing we need to know is the difference between withdrawal and consumption. Withdrawal means the total amount of water you pull out of a river or a well, right? And the important point is that some of that water, for some uses, you put back in the river after you've used it. Most of the water in Southern California for instance, that you're using for your toilets and your showers and your dishes is collected, cleaned up, and used again. So it's withdrawn, but it's put back into the system. Consumption is actually lost. It's stuck into the ocean. It's put into the atmosphere. It's actually water that's lost. So why is this distinction important? Well, the distinction is important because it shifts the emphasis about who the big consumers really are, okay? So this diagram shows that irrigation is responsible for 37% of withdrawals. So you can sort of think of that as a third. Industry is responsible for 41%. Industry plus thermoelectric power are responsible for 46%. So this looks like it's the biggie. All right. So public supplies, 12%, industry at 5%, and thermoelectric power collectively are 58%. And so most of it. All right. And so that's the sort of story that the water company is telling the residents of LA, right? But the withdrawals are dominated by these things. However, here's a picture. So that's withdrawals in the pie diagram at the top, and it's just what I said before. You got thermoelectric power and tan. You've got the public supply, self-supplied industrial, and so on, and the rest of these colors. And most of the circle is that, where irrigation's a big fraction, but only that big. The bottom diagram shows the consumption, and yellow, including the blue piece, all right, which is called groundwater abstraction. We don't need to think about that right now, but up to here, that yellow is irrigated agriculture. Industry, including thermoelectric power, is the purple. And it's because most of industrial water is used to cool machinery. And once you've cooled it, you put the water back in the river. Now, there are extra problems associated with that. You change the temperature of the river, all right? For a lot of rivers, that means you get exotic fish all hanging around the outflow from the evaporation tower, the cooling tower. But the point here is that this shows who the real user of water is. The real user of water worldwide is industrial agriculture. Like 3/4 or more of water is used by irrigated agriculture, full stop, right? And that is like doubly, triply, and quadruply true in Southern California, all right? So you've probably seen a picture like this. What's your water footprint? Everybody's always telling you to look at your feet prints now, right? Your carbon footprint, you know, what footprint? This is the water footprint. And this is how many liters of water are required for a cup of coffee, 140 liters, a kilogram of corn, 900 liters, a kilogram of wheat, 1,300 liters. So that's 1.3 tons of water for each kilogram of wheat. Soybeans, 1,800. Beef, big number, 15.5 tons of water to make 1 kilogram of beef, and so on. And so these numbers are just shockingly large. You'd think, my God, we're going to run out of water for eating beef. There are all kinds of reasons not to eat beef, all right? But the message here is choose more often to drink tap water, eat whole unprocessed foods, and reduce your carbon footprint by buying local. All right, now that's all great stuff. But the question you should ask is, what would happen to most of this water if there were no agriculture? Now, most wheat, for example, is rain-fed agriculture. You don't grow wheat using the complicated and expensive irrigation machines. You grow wheat in the middle of the plains where water falls out of the sky. And you can do the math, okay, of how much water falls that the plants actually transpire to make a crop and figure out what the yields are per square meter. And if you do the math, that 1,300 liters of water over a square meter of land is around 40 inches, a little more than 40 inches of rainwater. That's rain that they're talking about here. So that wheat is using rainwater and returning it to the atmosphere, okay? And that's what that number represents. Now, what would happen if we weren't growing wheat on that land? Let's suppose we turn it back into a buffalo commons, which I think would be mad cool, where you have buffalo migrating, and we got a great big game park out there. Well, it would be dominated by native species like big blue stem and switchgrass and stuff. And what would those plants be doing? They would be taking 1.3 tons of water per square meter and returning it to the atmosphere, just the way the wheat crop does, all right? So this is my point, is that it's possible to become convinced that there are water problems everywhere and in everything you consume. And as an educated Princetonian, you should ask yourself, is all of this true? And let's think it through. Now, in places where they're growing corn with irrigation water, especially if it's unsustainably withdrawn from groundwater, it really is true that you're taking a ton of water to make a kilogram of corn. That's a ton of water from a resource that's not replenishable sometimes. But, but there is a but, right? And in most places, you're not raising beef on irrigated water because it's too expensive, right? And so most of that beef, what that number represents is all of the alfalfa and grass and corn that the cow ate in order to produce a kilogram of beef. And of course, the cow is not just producing a kilogram of beef, it's producing kilograms of bone and neural tissue and all kinds of things that don't go into the beef. And much more important, the cow is using something like 90% of the plant energy it consumes just to keep itself warm, the way we do. High metabolic rate means that most of the energy just gets dissipated back to the atmosphere. So that really runs up the water total, right? The cow is returning a whole lot of water in its breath, but even more important, a whole lot of CO2 from plant matter that it ate that was fixed by plants transpiring water just to keep itself warm, right? Just to keep its body temperature up. So when you see claims that some food is a real water pig, view them with a degree of skepticism and ask, who profits from this, all right? And the simple answer is that there are all kinds of crops that we grow in places where water is scarce and we do it unsustainably. And great examples are in California, where we grow alfalfa in the middle of the desert because of a deal some railroad company cut with the California government in order to fix an environmental disaster. There's a whole story there I'll tell you about. It won't be till next time. All right, so that's the point. I think the water problem is one of the most severe problems facing humanity. You can't have 1,000 kids dying a day and not care about it. But on the other hand, it drives me crazy when I read stuff like this, that I know so much of it is just made up by a marketing firm somewhere. Pisses me off. Okay. So virtual water. What's the point about water? Well, how do you deal with water shortages then? And this is going to become so important when we face a future in which climate change takes rainfall that currently falls in places, and there are all kinds of people where it falls because there's food there, and it moves the rainfall somewhere else. If it's a transnational move, those people all of a sudden are in trouble and they have to become refugees, all right? And so what could we do for those people? Well, we could deal with the refugee problem more humanely. But if we actually want to give them the option of living where they currently live, In principle, we could move the water. But the right way to think about this is, wait a minute, what is that water used for? Well, to a first approximation, it's all used for irrigation, right? Almost all the water consumption is used for irrigation. And irrigation is used to make food. And so why don't we move the food? Where you could move a kilogram of wheat instead of 1.3 tons of water, all right? And so the important point is that the way to fix the way to fix water problems in general, after you've dealt with basic sanitation, for the tiny amount of water that people actually drink themselves, consume themselves, you can fix the rest of the distribution problem by moving food around, at least in principle. That's what the sort of scientist accountant would think to do. That's what an economist would think to do. Note, though, that this is the opposite of local food. This is big international trade in food that becomes commoditized and everything else. So local food that we cherish for community building reasons and because it feels healthier to us, that whole movement may be at odds with what we're going to need to do to fix global distribution problems, especially as they develop with climate change. When the distribution problems we have now become much more severe. Now, if you plot population size versus rainfall, population density versus rainfall, there's an amazing positive correlation. Like nobody wants to live in the middle of the Sahara Desert. Duh, there's nothing to eat, right? And so the relationship between water availability and population size is extraordinarily tight, and climate change is just about ready to screw that up, all right? And so we're gonna have to move the water around or move the people around, and a lot of times the people can't move around, so we're gonna have to move the water around. We can't move the water around, so we're gonna have to move the food around. That's the point here. All right, so let me talk a little bit about water shortage, and which is mostly food shortage now, right? So that's the message here, is that when you have a water shortage and you're running out of water, sometimes you're running out of drinking water. It's like super severe. But if you prioritized what you're really doing, if the drought is cutting the water supply even by a factor of 3 or 4, what you're really doing is cutting into the incomes of agricultural irrigated water users, or you're cutting into the food supply of people who need it. That's, for instance, what happened at the start of the Syrian civil war, when the worst drought in history caused the agricultural system to fail, and 500,000 people became food insecure and then went berserk, right? With reason, right? All right, so there are a bunch of different kinds of droughts. We tend to think about meteorological drought. There's not enough rain anymore. Rain hasn't fallen, and so that's a meteorological drought. But there's also a soil moisture drought. The soil is too dry. Well, why isn't that the same thing as a meteorological drought? And the answer is that soil moisture depends on not just inputs, precipitation, it also depends on evaporation. And so if the precipitation stays the same and is relatively meager, but the temperatures go up, evaporation goes up, and the soil can dry out and become unsustainable for, unable to produce enough food, even if the rainfall hasn't changed. So that's why those two are different. Hydrological drought occurs when there's enough water shortage that rivers dry up or reservoirs become lower and lower and lower. Like you've all probably seen pictures of Lake Mead getting to lower and lower levels and getting below the water intakes necessary for cities like Las Vegas. And finally, there's socioeconomic drought that is caused just by human development. It's possible for humanity to just move into a region and then continue, and without there being any change at all in the precipitation or evaporation, just change the withdrawals and the use patterns. So this is what these are the kinds of droughts that hydrologists talk about. We're mostly going to be worried about meteorological and soil moisture drought here. So one of the most famous episodes in American history, right, Grapes of Wrath, right, is the Dust Bowl. And the Dust Bowl was caused by a series of droughts combined with poor agricultural practices that let the topsoil get away from them. And there are complicated feedbacks such that if you start a drought, you get more evapotranspiration. So if temperatures go up, for instance, you get more evapotranspiration. You get more evapotranspiration, and the soil starts to dry out. The soil starts to dry out in a place, and it dries the air that blows over the soil, and you get positive feedback that makes a regional drought. So the Dust Bowl was all of this. And the social response was migration out of the Great Plains, right? So the most famous artistic chronicle of this is the Grapes of Wrath, right? And the Dust Bowl is still, the Dust Bowl actually, you know, in most places now, if you plot any climate statistic, you will discover that like the number of record heat days per year in a country. Every place you go, you do that, and you get this massive increase. There are 5 times more heat waves worldwide than there were 30 years ago, for example, all right? But in the United States, there are some records you can plot and not get a statistically significant difference because the Dust Bowl was such a severe local event. And there were all these records set in one part of the country from this thing that was centered in, well, centered there, but that hit most of the agricultural Midwest, or a lot of the agriculture, the dry part of the agricultural Midwest, 30s and 40s. So what's going to happen with climate change? I've got a little bit of time. As I said before, regional scarcity is going to rise because of decreased precipitation and increased temperatures, which increase evaporative water loss. This is going to be exacerbated by increased demand and groundwater depletion because as humans get more wealthy, they demand more food and food of a different kind, and also because there will be more people at mid-century. You've already seen this diagram. This is how much warming there is regionally for each degree of warming of temperature, and this is the mean annual change of temperature in different regions for 1.5 and 2 degrees of warming and 4 degrees of warming, which shows you that the north, the Arctic warms the most. The other diagrams that are at the centerpiece of the latest IPCC report, the AR6 shows this one. Annual mean precipitation change relative to 1850 to 1900. So this is the money shot here. You can see that with 1.5 degrees, you get some drying in the American West, drying across the Amazon, drying in Eastern Australia, drying in Southern Africa, and drying in the breadbasket in Southeast Asia, all right? And then drying across the Middle East and Mediterranean. So those are the regions that'll be hardest hit with 1.5 degrees. You go to 2 degrees and you get mostly the same story. You go to 4 degrees and you get mostly the same story. But of course it becomes more and more and more severe. The bottom panel here shows the annual mean total column soil moisture change. This is what plants see. This is what the agricultural system actually sees. And what it does is it integrates both this temperature, both the precipitation change and the warming effect from the previous slide, which then causes there to be more evaporation. And there you can see that for even 1.5 degrees, we've got problems in our breadbasket and throughout Mexico and Central America, and big problems in the Amazon, and also problems in Southern South America. Big problems across the Med and the Middle East, big problems in Southeast Asia, big problems across Australia, and big problems in Southern Africa. So this is a win. This is 1.5 degrees. 2 degrees and 4 degrees, it just starts looking like crazy land. You can see the Amazon. The Amazon disappears if we get to 4 degrees mostly. burns up. All right, so this is, to me, this is the most severe. You know, people talk about tipping points, and I don't need a tipping point, okay? This is bad, all right? And so we're trying to avoid the right-hand side or even the middle, right? You can see the difference. It just becomes more and more and more severe the further along we go. Okay, well, I'm out of time, so thank you all. I'll pick up the rest of this lecture. See you guys.